Another common misconception about covariance or correlation is that it doesn't imply causality or causation. No, causation is a very important concept, which is very useful to know because it means that you understand the problem very well. Um, so causation means that X is going to cause Y, right? So let's take a look at these examples. So the first one, if you look at the yield of oranges and apples in the Monterey Valley in California, you would see that they're highly correlated. Okay, but it's not that the fact of having more oranges will give you more apples. It's clearly not the case, right? It's the most likely explanation of their high correlation is that if you have a lot of oranges one year, it's probably because the weather was really good, and the weather affects both apples and oranges, right? Um, so that's one typical mistake one makes when you find a high correlation, a correlation of 0.9, you're excited because you might discover that variable X is causing or is explaining variable Y. But it's not always the case. And this is a perfect example, right? And this is a case where there's a missing variable, which is the weather, that affects both. The second example, there's a high correlation between the number of police officers and the number of crimes in a given city. Therefore, you might want to think that to reduce crimes, one should reduce the police force, right? Which, of course, doesn't make sense. And the relationship in that case is reversed, right? So again, you find big correlation, but you really don't know if X is causing Y or Y is causing X. All right, there's more examples like this. Just click on that link. The solution to this problem is way out of the scope of this course, but it's called controlled experiments. Okay, so if you really want to know if there's causation in a given problem, you would have to do controlled experiments. All right, so you have two populations, identicals, and to one you give the experiment or like typically it's a drug, right? You want to see if a drug causes people to get better. So one group you give the drug, the other you don't, and if and only then you're able to establish causation. Okay, so besides from the covariance representing the linearity of the relationship between X and Y, the covariance is also useful to computing the variance of linear combinations, which we're going to do a lot in this course. Okay, so let's start with some notation. So from now on, we're going to use a vector notation when we refer to these n random variables, x1 to xn. Okay, so we're going to play now with these type of random vectors, we're going to call them, and we'll use the bold notation for vectors or matrices. Okay, you can think about this vector as a collection of n random variables, right? So maybe you take a survey and you have n people, and that's the x1 represents the answer by the first person to a particular question. Okay, this would be the collection of all the answers. All right, but it could be any random variable, right? The weight or, but each one associated to each individual person in your sample. Okay, so this is our vector x. Now, we're going to define these variables. Mu I would be the expected value of xi. Same for the variance. Now, the new notation is this one. Now, the covariance between xi and xj, we're going to call it sigma ij, like a shorthand notation. Okay? And rho ij is going to be the correlation right? And we know that the covariance is the correlation times the standard deviations. Just my definition. Okay, and it will be convenient to define what we call the variance covariance matrix, or just the covariance matrix. Right, so the symbol we're going to use is this double barred C, okay, to make sure we understand it's a matrix. So if you see here is the formula for really the variance of x, right? So if you take the bold out, the expected value of this would be like the variance, right? X minus mu squared. So in vector notation, right, the t would be the transposed, right? So this would be like the x minus mu squared in scalar. So C of x is a matrix. It has these interesting properties. So it's symmetric, right? So for example, this term here, rho 2, 1, sorry, sigma 2, 1, so the covariance between x2 and x1 is the same as the covariance between x1 and x2, right? And that's the property of covariances. It doesn't matter which one goes first. So that's why this matrix is special like that. In particular, this lower triangular matrix right here is the same as the upper one up here, just transposed. Okay, and then, oops, I'm trying to highlight here. The terms in the diagonal, if you see, they're all the variances of each xi, right? So sigma 1 squared right here, by definition we said is the variance of x1. Okay, so the diagonal gives you all the variances of each variable, and the off-diagonal terms give you all the covariances. So it's a pretty compact way of expressing the covariance of a vector. All right. Now let's define linear combinations. So this would be one linear combination. U or W is the same but with different coefficients. All right, so in general is a sum of constants, AIs in this case, times a random variable. Okay, in vector notation it would be A transposed times the vector X. And A transpose is this row vector, right? Well, transposed. So it's just a collection of coefficients A1 to AN. Same for B. So for example, the most famous linear combination in statistics is the sample mean, or just the mean, the average values. So for the average, let me call it A for average. It would be, we all know the sum for average, right? We divide by the number and then we do the sum of the xi's, okay? So this is the average of the x's, obviously, and this is one type of linear combination, right? And in this case, all the AI's are 1 over n, right? Because you could write it inside the summation, obviously, and it would have the form right here, right? The sum of a coefficient times random variable. So all the coefficients are 1 over n. Now, another very famous one, right, is just the straight sum. So just the sum of xi's. Let's call it S here for sum. In which case, all the coefficients are obviously 1, right? So that's the interpretation of linear combinations. Simply a sum multiplied by some coefficients. All right? Okay. So we have these two linear combinations, u and w, and then the covariance turns out to be this expression right here, which in compact form is pretty nice. So is the coefficients A transpose times the covariance matrix times B. Okay? In standard form, that's the expression, so double summation. Okay, and this number is a scalar. So it's a number. It's not a matrix or a vector. Okay? It's just like the variance of x. Okay, so let's see why this formula is true, and then we're going to do examples about it. So there's two ways of doing this proof. But let's start with the definitions. All right, so given these two definitions of u and w, we can calculate their expected values. Okay, and we know expected values are linear operator. So let me do w here. So if I do the expected value of w, it's going to be expected value of this whole thing, and the expected value operator comes inside. So it's going to be bj times expected value of xj. But by definition, the expected value of xj is mu j, right? So that's why we have this. And in vector notation, it's simply b transpose times u. Okay? So that's the expected values. Now with the covariance, in vector notation, you can follow this line of reasoning, but yeah, so we replaced by the definition here, we just computed the expected values of each, simply replacing x by mu, right? All in vector form, by the way. And the same thing for w, and then we factor the coefficients, and we notice that that's the very definition of the covariance matrix. So that's the result that follows. Okay? And this is the same proof, but with standard notation if you're more comfortable. Okay, so a very important corollary of this fact is the variance of a linear combination. Okay, because we already know that the variance of x, not in vector form, or could be in vector form, is the covariance of x with itself. Right? So we're going to apply the same thing here. So if we're compared to the previous formula, excuse me, so the covariance of u and w is A transpose covariance matrix times B. But if we put, instead of u and w, you put x and x, it's going to be like this. Or I should have said u and u. The covariance of u and u, which is the one that uses A. So this, you could say this is the covariance of u and u. U as defined in the pages above, right? Because yeah, this is u, right? But that's how we defined it earlier. All right. So applying the formula we just learned is C transpose the matrix, and then we had B, but since now it's u and u, now we put A again. All right, so pretty much the same formula. Now in standard notation, this formula has a nice insight. Okay, so it turns out that we can express it in this way, which we're going to explain in a minute. But notice that here we're doing, first, these are just the diagonal terms of the matrix that we just talked about. And these are all the variances of the xi's, right? So the first term is the sum of the variances of all the individual xi's times these coefficients. Okay, but then we have 2 times this double summation, which will make sense in a minute, I hope. which importantly is 0 if all the xi's are independent, right? Because we have, this is the covariance of xi and xj, right? And we already know that if two variables are independent, their covariance is 0. And that's what's going on here, right? If all the xi, xj's are independent, this double summation term would be 0. All right? And this formula has this name, propagation of error, in the literature that you might have heard of. And basically it means that if you have errors, and by errors we mean variances, typically, or covariances. So when you have errors in the xi's, and the xi's are the input of some system, right? The output, which is represented by this linear combination, right? That's kind of the output of your process. The output would have an error that you can calculate with this formula, okay? And when things are independent, you see that the error is always tends to be greater than the simple sum of these of the xi's. So that's a way in which the errors propagate, so to speak. And we're going to see examples of this. Okay, and let me give an intuition of where this formula comes from, right? So we start with the definition of U, sum of the xi's. For the variance of U, right, just the covariance of U and U's, we just said we apply the fact 2.9, so it's the formula for the covariance of U, which is just A transpose covariance matrix times A. Right, which in standard form is like this. And then this is the kind of the key steps that we're going to do. And these are taking into account the properties of the covariance matrix. So for the first arrow there, we're using the fact that the diagonals, remember, of this matrix gives you all the variances of the xi's, right? So the first term, so notice this double summation, right? Each term in this double summation is the covariance matrix. Well, the covariance, like this would be the number in this matrix at row I, column j, right? Which might be this one, for example, right? When I is 2 and j is 3. So all these covariance terms are given in this matrix, and we're just multiplying them by two constants. Okay? So the structure of this sum follows the structure of this matrix. That's why we're doing this. So first we do the summation of the diagonal terms. Okay? And that's the a squared times the variance. Right? We're adding this plus this plus this times the corresponding coefficients there squared. Right? It's making I equals j in this summation. Okay, so that gives you all the sum of these two, this diagonal. And then these are all the off-diagonal terms, right? We do the same double summation, but with j not equal to I. All right, that's key here, right? So first we're doing the summation of the diagonal, and then we're doing the off-diagonal terms. And in the second arrow right here, we just notice that since the matrix is symmetric, you can do the summation in one of the triangles, either the lower one or the upper one. And then you can multiply it by 2. So that's what we're doing here. Right, and here, this is the key, is that j starts from I plus 1 now. Right, so if I is 3, so right here, in this row, then we start at I plus 1. So we start at this term right after the diagonal. So it would be right here. Right? So in this case, this summation applies to the upper triangular matrix here. And we multiply by 2 because there's 2 such triangles in that matrix. Okay? So this is the most useful formula for the variance of a linear combination. And again, it's first is the sum of the variances times the AI squared, so the diagonal here, and then twice one of the triangles. Very good. Now let's take a look at very important results from these simple formulas. All right, so here we have, let's focus on these two first. So the variance of x and y, x plus y, or x minus y. Now if we apply the previous formula, let's go little by little. So let's do f variance of x plus y. Right, so this is a linear combination of x and y, right? Or we could have done x1 and x2 plus x2, but it's the same. Okay, so here's the case where it's a simple sum, so the coefficients ai are all 1. Okay, so the diagonal term, right, the sum of ai squared times the variance of xi, in this case, would just be the sum of the variances, right? Because times I squared, or 1 squared is 1. Okay, so yeah, simply 1 squared times variance of x plus 1 squared again, variance of y. And then plus twice the covariance of one of the triangles, right? But this is a 2 by 2 matrix, right? So there's only 4 elements, right? So here you have the variances, and there's only 1 covariance, right? So that's why, and it's the covariance of x and y, obviously. This would be the covariance of y and x, which are the same, right? So that's why we have here 2 times, let's put the AIs and AJ, right? So AI is 1 again, AJ is 1 times covariance of xy. All right? So, and the same thing for the second one, but in this case, right, for x minus y, it's all the same. 1 square variance of x, yeah, extra parentheses there. Here's the same, but let's just write it out, right? The coefficient ai for the y is -1, but squared it remains the same, which is unfortunate. We'll see why. And then the same thing. So let's do plus the formula times the ai1 times the other aj -1 covariance of xy. And you get this, right, which has the minus sign there. Okay. And now, so the most famous version of the propagation of error formula is when x and y are independent. So if x and y are independent, so it means that the covariance of x and y is 0. And therefore it means that the variance of x equals the variance of x minus y, right? Because it's just the sum of the variances. Okay, and now this might not be intuitive, right? Because in one case you're adding 2 random variables, in one case you're taking the difference. So you'd expect that the variance of the difference might be smaller, but it's not. It has the same error or variability risk, right? Which is not intuitive. And mathematically it is explained by the -1 squared here. Basically, since you're squaring it, it doesn't matter whether you add it or subtract it. But it gives you this intuition that no matter what you do in the system, your error tends to grow, right? Regardless of if you, in this case, add or subtract. Now, when they're correlated, this is not going to be the case, right? So you have to adjust with the covariance systems. All right, very good. So please try to do these two. Are quite useful as well. So this is a linear combination of one random variable x, and a and b's are constant. The same for y here, right? So try to see why that is true. This right here, well, is the same variables here. They're a little too small, but that's for the correlation. Very good. All right, so now we have a bunch of examples to go through. So actually, let me start with the last one. And then we might work our way up. Because it uses the exact same formulas that we have fresh in our heads right now. Let me check my timing. All right, we're good. So this might be useful. I think it's good to know a little bit about how stocks work, how portfolios. So this is one of the simplest models in finance to choose stocks on the market. Okay, and this is a perfect example, really, in this way, because here we're going to define the xi's as the rate of return of stock I. Okay, so in the market there's millions of stocks, right? One for every company, and the rate of return is simply the percentage of growth of the stock price in a given period. Okay, so it's typically a percentage. Right, so it's the final value divided by the initial value in a month or a week. So we're going to do it a weekly, I think. Right, so the mean of xi's are the expected rate of return. So typically it's around 10% annually in a good economy. And then the standard deviation of xi in finance has this, they call it volatility, right? But it just means the standard deviation of the xi's in this case. Okay, so a portfolio is just how many of each of these stocks you have. So let's say that there are n stocks, okay? Then you need to choose how many of each you buy, given a constraint of your the amount of money you have, right? So the linear combination U here, right? That's the value of your portfolio, and the AIs in this case represent the proportion of each stock that you have, right? Like if you have 10% of Facebook shares, then AI would be 0.1, right? And that's the value of your portfolio, right? And the value, again, in terms of the rate of return, because that's what you want to maximize in these cases. Okay, so that's, I think this is a clear example of how to apply and understand the meaning of these linear combinations. Okay, so the AIs are, we can call it weights, right? So between 0 and 1, and they need to add up to 1, right? Because you want to use the whole money that you have. All right. So the risk is typically the variance of your portfolio. And in this case, just the variance of U. And this is the formula we just discussed. Okay? Now, what we want to do here is in the same way, it's like the casino problem in the midterm, right? So we want to minimize the risk. So we want to find the AIs such that they would minimize the variance of your portfolio. Okay, so that would be kind of the simplest way of choosing your investments. Okay, and remember this formula, right? Now, stocks are not independent, so this is not going to be zero in our case. But it's good news, right? Because you want to minimize the variance, right? So this term, it's everything is squared here, so it's going to be hard to minimize. But this one is kind of easy because remember, at least in terms of intuition, these are the covariance, right? Covariance of xi, xj. And again, rate of return of Facebook shares and rate of return of Google shares, for example. All right, and those are independent. So if you want to make this variance minimum, you want to choose I and j such that this is negative, right? Because if it's negative, then this plus sign will actually be a negative sign. So you're going to have the first term, which is hard to reduce, but then we can subtract all the terms here hopefully with all these negative covariances so that you can actually subtract from the variance. So that's a nice intuition because it means that if you want to minimize risks, you should have stocks that are correlated in this way, so negatively correlated. So if one stock price goes up, then the other would go down, or vice versa, which is what you hope for, right? Right? If one goes down, then the other one will go up, and that's going to maintain a little bit the variance of your portfolio value. Okay. Yeah, this is the same matrix, right, that we've been talking about. So now let's consider this data. Okay, so these are weekly returns in this period. And this is actual data, by the way. So famous stocks, right? As Google, Apple, Facebook, Twitter, Tesla, Microsoft, and Netflix. These are the mean returns. These are the volatilities, and these are the coefficient of variations. So just the ratio of the two. Okay. And these are just graphs of these numbers, just to give you an idea. Now, let me call to your attention to the coefficient of variations. Remember how we said that the rule of thumb is when this guy is less than 0.3, we say that it's moderate risk variable. And if it's greater than 0.3, then it's kind of very unpredictable. So look at the magnitude here. The smallest one is what? This one, right? 4.6, which is huge. And that's what is a characteristic of stock prices. They're very, very unpredictable, right? That's why it's so difficult to have a, like a silver bullet and always make money. So these are huge variabilities, right? And it's also because it's weekly. So if you did it daily, it would be even more variable, more unpredictable. So there's a time component also in this. All right, so just to give you an idea of the type of coefficient of variations that we have in these things. All right, so we have all that data. This is just a graph of, you have the volatilities or sigmas and the coefficient of variations for the different stocks against mu, just to see if there's a relationship. no biggie. Okay, this is the covariance matrix. So it should be like this. Well, actually here. But this is in color, so you can appreciate kind of what you should focus on. So, and this go from 2 to 50. Okay, so red means a higher correlation, and 2 is the lowest. Okay, now there's no negative correlations as we see here, but that's okay. And remember, so this is the covariance matrix. So in the diagonal, so these guys are the variances. So here we see that stock number 4 is the one that has the most variance. Let's see quickly which one it is. It's Twitter. Right, 7 something. That's a standard deviation. Right, 7 squared is around 49, of course, so that's that value. And so on and so forth, right? And also you can see at a glance all the covariances. So the wider ones, like this one, 7 and 3, they are very low or uncorrelated almost. So it's value of 2. So 7 and 3 are Netflix and Facebook. So that's saying that, like, remember, we cannot say independent, right? Uncorrelated doesn't mean independence. But we can just say that if one price, so if Netflix goes up, there's no reason why the other stock would go either up or down. Something like that. Okay, and these are the real numbers of that matrix, because we're going to need them to do our calculations. Okay? All right, so part A, if you only buy from Netflix and Facebook, what are the right weights? What are the coefficients AIs? Okay? All right, so Netflix and, so it's 3 and 7. So 1, 2, 3 is right here, and 7 will be 1, 2, 3, 4, 5, 6, 7, the last column. 7. Okay? So, yeah, that's the covariance between the two. This is the variance of Facebook. That's the, Netflix. That's the variance of the last one. Yeah, Netflix and Facebook. Netflix at 7. Okay, so those are the numbers we're gonna need, right? And again, remember, this is symmetric, so this 3.2 here is the same as this one, right? These are symmetric. Okay, so we're gonna use our formula here. Right, so first we add the diagonal terms, and then 2 times the covariance. That's it, right? So in A3 and A7, they are the weights that you need to find. Okay? So variance of X3 is 8.2, right? As you see here, variance of X7 is 27.7, right? Right there, and then the covariance is 3.2. Okay? So no surprises here. Then you rearrange it a little bit and you get this expression, okay, which is only a function of A3, because, right, A7 is 1 minus A3, right? Because we need that the sum of both equals 1. Okay, and then we have to find the optimum value of a function. So in this case, the minimum, right? You want to minimize the variance. So if you recall calculus, you're going to take derivatives and set it equal to 0, make sure it's a minimum, not a maximum. Or you can always graph it, right? we can graph A3 versus the variance of view, and then hopefully it will look like this, and then that's the value, the optimum value A3 star, which in this case is 0.83. Okay, so that's your optimum values. And part B is what are the expected return variance and coefficient of variation, so which is simply evaluate the formulas of each with these coefficients. All right, so for the variance, we just plug in the right value for A3 here. Same thing for expected value. Yeah, so make sure you can get those. So that's expected value, variance, and coefficient variation of that stock. All right, then we repeat for Apple and Twitter. I'm sure you can do that. Make sure you get the same. All right, and then part B, which one do you recommend buying? Again, we recommend buying the one with the smallest variance. You know, given that the expected return is about the same, right? You don't want to choose the minimum variance if the expected return is really low, right? So what you want to do is compare them both in terms of expected value and variances. And then really there's no silver bullet. It's going to depend on each individual feelings about risk, actually. All right, so there's no right and wrong answers to this one. Okay, we have time for one more example, so let's do this one. This is a more traditional one. So here we need to calculate the covariance of x and y, and we're given the joint PMF as usual, right? So we have the sum totals, and they add up to 1. All right, so this is a case where the covariance will turn out to be 0, but then we cannot say that they're independent, and we'll see why. Okay, so for the covariance of x and y, so we already know the formula, right? It's the expected value of x times I minus expected value of x times expected value of y. Right, so no linear combinations involved in this example. Excuse me. Okay. So we need to compute all of these. All right. So e of x and e of y, I'm assuming we all know how to compute it, right? Because if this is y right here, this value is summing across x, so it means that this is actually the marginal of y. And here is the marginal of x. P of x of x. Okay? So yeah, these we know how to calculate, right? So now for this one, x times y, so it's this expected value of a function. Remember the formula is, so here we have two variables, so we sum across x and y, well, little x and little y, of the function, which in this case is x times y, times the probability, the joint probability mass function. That's by definition of the expected value of a function. Oops, all right. And this is simply going around the PMF here. So we can do it in one shot or two shots. Let's try one shot. By that I mean, so we're going to go each term of the body of the table here and multiply by the function. So we start here, that's the 1 over 16. So the x value corresponding to that is -1. Then the y value is also -1. And times the probability, which is 1 over 16. Then plus, right, because we have this double summation. We continue here. Plus, now you do the second term. Corresponding value of x is 0. Corresponding value of y is negative 1 still, times 3/16. All right, and then you keep going. All right, you do this term, then you're going to do this one, all right, till you get to this one. So let me do the last one. Value of x is 1, value of y is 1 as well, and probability is 1/16. All right, so if you do this calculation correctly, this should be 0. All right, so this term is 0. Now, it turns out that if you do these guys are also 0, expected value of x and expected value of y. Now, maybe you can see it directly, right? So it's going to be negative 1 times this plus 0 times this plus 1 times this for the expected value of y, right? So, since you have the same weights, if you do it, you're going to get 0 for both. So please do it, make sure. So finally, the covariance is 0. And you might want to say they're independent, but they're not. Why are they not independent? Because for them to be independent, we've discussed several times that any value in the body of the table, so the PMF should be the product of their marginals. So 0 should be the product of 3/8 times 3/8 if they are independent, but they're not, right? So they're not independent. And you only need to show that that happens in one cell for the whole thing not to be independent. So in this case, 0 is not equal to 3/8 times 3/8. All right, and I'll see you in class.